Okay, good morning, everyone. For those of you that are watching online and don't know me, my name is Brian Strange. I'm a UPM professor, and I'm coordinating the neurotechnology initiative that we have at this university. Just a couple of updates on the initiative. Things are going well. We have as you know, that you're here for our second big seminar from our seminar series in neurotechnology. We have now a network, a cátedra, red de estratégica based at the UPM in neurotechnology, which is work through the eBrains node of Spain. And there'll be some exciting short videos that we'll be releasing soon of some of the major people involved in the neurotechnology initiative. So today, without further ado, we have José Garrido that has come from Barcelona to talk to us here at the UPM. We're in the Centro de Tecnología Biomédica. And the best person to introduce José is a former colleague of his from the UPM, where José trained, Fernando Calle. I'll pass you to Fernando Calle, who'll do the introduction.
Thanks, Brian. I guess that's okay. So even if the presentation of the NEUROTEC Technology by Brian was in English, and the conference by José will be in English, but I would like to introduce him in Spanish. Conozco a José desde hace más de 25 años, cuando él estaba haciendo su ingeniería en telecomunicación, a la que siguió una tesis doctoral tratando problemas de ruido. A él le interesaban las señales pequeñas, las relevantes en telecomunicación. Hizo una tesis muy notable. Después marchó a Alemania. Allí todos le llamaban Paco. José Antonio a lo mejor era muy largo. Hizo un trabajo estupendo con diamante. Diamante sigue siendo hoy uno de sus objetivos, porque el diamante como material extremo tiene muchas posibilidades. Pero enseguida se dio cuenta del potencial del grafeno. Ya incluso siendo líder de un grupo relevante en el Instituto Walter Schottky en la Universidad Técnica de Múnich, él decidió compaginar estos dos materiales basados en carbono, diamante y grafeno. Por razones familiares, supongo, tenía ganas de volver a España. Desde la UPM no fuimos capaces de ofrecerle lo que él se merecía y finalmente quedó en Cataluña, donde ahora él es profesor del ICREA, subdirector, yo no sé si del Centro solo para Innovación o bueno, del Centro del Instituto de Nanociencia, del Instituto Catalán de Nanociencia y Nanotecnología, el ICN2, donde está haciendo un trabajo fantástico en neurotecnología. Y de hecho él es líder de uno de los Work Package de la flagship del grafeno, el dedicado precisamente a esta temática. Esto le permite aún así fundar una empresa, InBrain Neuroelectronics, que es una empresa bastante exitosa y que está levantando un montón de capital. Estoy seguro de que también en la parte industrial José va a triunfar. De todas maneras, le sobra tiempo. Y lo sé porque lleva unos cuantos meses organizando una petición de mucho calado dentro del PERTE de semiconductores, que como sabéis es una de las iniciativas mejor dotadas de las que últimamente están viniendo con recursos europeos. Él, me consta porque he tenido la oportunidad de conocerlo, ha escrito una propuesta grande, sólida y convincente, y yo deseo que salga adelante, porque puede cambiar el panorama de las infraestructuras de microelectrónica en España. Todas estas cosas son parte de sus virtudes como ingeniero, pero también como científico. Aún así, la principal es que José Antonio, o Paco, es una gran persona. Y esta es la principal razón por la que yo he decidido venir hoy a presentarle. Gracias, José Antonio.
Primero, Fernando, muchas gracias por tus palabras. Estoy completamente rojo. Brian, thank you very much for the invitation. It's a pleasure to be here in NEUROTEC. I was not sure about how to prepare the presentation. I hope that it's not too long. I would like to share with you what we have been doing in the last years on neural interfaces using graphene technology. And Fernando mentioned already the disclaimer. I have interest in a company, so part of what I'm going to present has been transferred to a company, so I might have interest in what I'm saying about that. Yeah. So when the audience, I guess that it's a mix between experts in neurotech, maybe others who are not experts in neurotech. So I want to tell you what neural interfaces are from my perspective. I was mentioning to Brian and to Fernando that I was in the last 2 days, there has been a workshop here in Barcelona, in Madrid on neurotechnology. Neurotechnologies and neural interfaces, and there were many talks discussing or people discussing about the future of neurotechnology and the impact on society. If you think of neural interfaces, these are devices which are already in the clinic. Some of you might be aware with some of them, like cortical electrodes for monitoring during intraoperative surgery. We have deep brain stimulation implants to treat diseases or disorders like Parkinson, spinal cord stimulation for chronic pain. And when you think of all of these devices, there is a medical need. Yeah, there's a clear medical need that is the driving force of why I'm doing this. You could think of some of these devices could be used to discover new biomarkers. If you think of some disorders or diseases, you would like to monitor them over the course of progression of the disorder. And some of these devices can be used for that, not just for the treatment, but just for monitoring. Of course, they can be used as a neural prosthesis. In the case of patients with motor or sensory disabled conditions like deaf, blindness, spinal cord injury. And I think that's something that it is a common topic for many of us. It's like we would like to understand from a fundamental point of view, how the brain works. So having technologies that allow you to do that, it's something very, very relevant, no? Despite many of these technologies are in the clinic, and we were commenting with Brian before, it is surprising how they are still based on quite legacy concepts and technology and materials. Yeah, and if we want to go and to advance and to make sure that these technologies have a real impact and a broader adoption in patients, we need to introduce new materials. We need to introduce innovation. And innovation in this case, it's complex because when you think of what are the materials that you could use in this type of environment, which is very harsh, there are stringent requirements. No, they have to have. You need to use materials which are very stable, chemically stable. You need to use materials which are biocompatible, and you need to use materials that can allow to do what you want to do, which is to interface the nervous system, either recording from the system or stimulating. No, and this is one of the challenges. I want to start by saying that what I'm not interested personally, it's on this. Yeah. There is a tremendous hype in the field of neural interfaces on what or how to use these neural interfaces. No, like you want to control your mobile, no, as if you could not just use your hands or no. But anyway, so this is not what you're going to. What I'm interested. This is not the area that I want to explore. What I want to do is just to share with you this type of application. Also, this is a patient with Parkinson that has implanted a device, and now he's showing that he's going to switch off the device that he has implanted. And you can see that immediately this patient starts to suffer from tremor. There will be dyskinesia. There will be some rigidity that he will deliver in the course of a couple of seconds. And you will see, if you could hear his voice, he's trembling, he cannot talk properly. And eventually he decided it's enough, I'm going to switch on the deep brain stimulation. He switches on and then it recovers, right? So this is what is driving the research that I'm doing. And I think that many of the, and some of, probably for many of the people in the audience, and this is the case where things are working properly. It's not always the case, yeah, and I will try to explain why this is why this is not always working, yeah. So when I think of what are the challenges for neural interfaces, when you think of bidirectional neural interfaces, you want to record and you want to stimulate, you want to communicate properly with the nervous system. I typically think, and this is my personal view, yeah, on three main challenges. On the recording side, either or whether this is brain or like a central nervous system or peripheral nervous system, you're going to be dealing with very small signals, yeah. And if you want to add to these small signals, if you want to add spatial resolution, if you want to measure from with spatial resolution from different areas, you will need to miniaturize your sensor. So we know that when you have a very small sensor, the noise increases. So small signals, reading a small signal is very challenging, yeah. And not all the electronics that you can have are going to be able to do that. The second challenge, it's like a stimulation. In order to deliver a therapy, you need to stimulate the nervous tissue. And we do this by, there are different ways, but in this particular case, and I'm going to present is electrical stimulation. There are other ways. If you want to do electrical stimulation, we typically do using a concept which is capacitive stimulation. You try to design a device which behaves as a capacitor. A capacitor can store charge, but it can also deliver charge. And when you think of the amount of charge that you need to deliver to the system in the form of an electrical impulse to stimulate it, as an engineer, this is massive, the amount of energy that you put into the system, the amount of current. And not all the materials that we are using are capable of delivering that charge. Yeah? So that's also a challenge. If you want to change or you want to innovate with respect to the current materials, you need to make sure that the ones that you're going to be using are capable of doing that. And the third challenge, what I think it's very relevant as well, it's about invasiveness. I mean, invasiveness is one of the reasons why there is more patient rejection. You don't want to get like a large device being implanted into the brain, or with a cable going down your neck until a pacemaker, large pacemaker that is implanted in the chest. You want to miniaturize. And you also want to make sure that the devices that are in contact with the tissue, the mechanical properties are compliant with the mechanical properties of your nervous system. Yeah. And this is also, in my view, the way to do that is to make sure that everything that you deliver or that you develop is based on flexible electronics. So again, this is putting some limitation on what are the materials that you can use. No. There are many solutions to these three challenges, and I'm not claiming that this is the only one. I'm sure there are other solutions in the field nowadays. Currently, the clinically available technologies are based on metal and classic platinum iridium metal, and there is a need to innovate on these material. I'm presenting that graphene and other 2D materials offer some advantages in the field. In particular, you can integrate it, and I will show you this with flexible electronics. It is a material that can be can be designed in a way that you can deliver large amount of charge, and at the same time, if you do things right, you can develop sensors which are very sensitive and with a very low noise. So that's why we were interested in this material. But as I said, I'm not saying that this is the only material. There are organic material that are also being explored by other researchers. I will just mention about recording and stimulation capabilities, and to start with the recording, with the challenge one, let me just share with you what the challenge is. So this is a graph that shows the spatial temporal space that you need to cover if you want to address properly brain activity. Yeah. On the left, on the y-axis, you have time, and the x-axis, you have space. Time, if you are interested in the understanding how individual cells are boosting activity, you would be looking into the kilohertz region, yeah, milliseconds. If you are interested, for instance, in memory aspects, or this will be in the tens of seconds, or in the region of seconds. So you can see all the from milliseconds to tens of seconds. You will need to deliver or develop technology that can do that. On the spatial resolution, you might be interested in exploring whole regions of the brain, for instance, and I will show later on, if you want to develop like a language, like a speech as artificial devices. Language is broadly distributed on the brain. So this is we're talking about centimeter scale. And if you are very interested in some motor neuron, the one single neuron, we are in the micrometer scale. Yeah. So this is what you need to develop a technology that can cover all that space. And there are different technologies to do that available. And I'm just going to focus on electrical recording and electrical stimulation. And then regarding the level of the signals that you're going to measure, there are different ways to access the brain signals, either from the scalp. These are called electroencephalography. Typically, you have signals that maximum frequency that you will get is of the order of tens of hertz. And they are very small signals, microvolts. If you get closer and closer to the brain tissue, you gain spatial resolution, and also the signals, the intensity of the signal will be increasing. So we can reach hundreds of microvolts, in some cases a few millivolts, and you can reach up to one kilohertz. Yeah. So I will show some technology that are addressing different areas in the brain. This is the only slide which is very much on engineering, my background. So there are two ways you can record from the brain, electrical signals. Yeah. One is using what we call passive electrodes and active electrodes. Yeah, a passive electrode is simply like a piece of metal or a conductor that is going to monitor like electrical activity. Yeah, and it's interesting because when you think of you have this is your what we call here a microelectrode array. This is, let's say, a piece of metal which has certain impedance, and you need to measure that electrical potential there with let's say an amplifier, whatever. It's a system that measures voltage signals, right? But it happens that the electrical, the coupling, the electrical coupling between your electrode and your amplifier is such that at very low frequencies, yeah, the impedance of your electrode that you're using, your metal, start to increase. It's a capacitor to increase higher and higher and higher. And eventually, the gain of the whole system as a function of the frequency. So the gain of the coupling between your electrode and your amplifier drops and drops. So what I'm trying to say is that the gain drops means that you cannot measure signals at very low frequency. Yeah? That's one of the challenges of using passive electrodes. On the other hand, there is another concept, which is for active electrodes, which are a transistor. So it's a device that has two terminals, and the conductivity of the transistor is changing when an electric field in the vicinity of electric potential changes. Yeah? That's an active device. And because of the electrical coupling between that device and the amplifier that you use for measuring is such that it would allow you to measure down to very low frequencies. Yeah. So passive electrodes, they have a drop in the gain, and low frequency active electrodes, they don't. And why that's interesting, I just want to show why I'm dedicating some time here. And it's because the spectrum of brain signal that you want to measure cover from high frequencies. Yeah, this is the ultra fast region, and even going towards the single unit activity, individual cells, down towards lower frequencies to a region where only active devices are capable of measuring. Yeah, and that's why we also favor the use of some active sensors in our devices, and where graphene plays a role, as you will see later on. Yeah, so we will be using active sensors based on graphene because of this capability to measure low frequency. Another challenge on why we're using graphene and this type of active sensors is the concept of the number of channels. I mean, if you see here, for some of you, this is a picture in which these are array of large electrodes, passive electrodes that are used to monitor during before you do surgery in patients with epilepsy, before you want to do resection. Yeah, and you see how complex is to put this is probably like 64 electrodes with all this wire. Every electrode has a wire. If I want to scale up from 64 to 1,000 sensors, this is a very nice paper showing 1,024 electrodes that can be integrated using thin film technology. However, what is not shown in this paper, or is shown but in the supplementary, is the connector that you need to use to connect your thousands of sensors to the external wall, because thousands of sensors have thousands of wires, and this is that's not feasible in an implant. What you can do is you can use the concept of multiplexing. Multiplexing is a concept that I can build an array of sensors, and instead of measuring from each of them at the very same time, what I can switch very quickly between sensors. Yeah, so that's a concept from electronics, and in that way you can dramatically reduce the number of wires. So imagine that you have an array of m times n sensors. So if you use a non-multiplex concept, you have m times n lines, right? And if you have a multiplex concept, you have n plus n lines. No? So if you're thinking of scaling up this to thousands of sensors, it is very important to do that. And not all the materials would allow that type of multiplexing concept, because you need to switch very quickly between them. Okay, so this is where active sensors are preferable with respect to passive sensors. So what is the sensor that I'm going to present here? Is based on a field effect transistor I mentioned before, and this is just the concept of it. It's a device that has 3 terminals. This is going to be based on graphene, and I'll show later. So a layer of graphene between 2 contacts, and we're going to be passing a current between these 2 contacts, and that current, conductivity of the sensor, depends on the electric potential in the vicinity. Yeah. This is the 3rd terminal, what we call the gate. So any variation of the electric potential coming from brain activity would be able, or would modify the conductivity between the drain and the source. And this is what it's shown here. Here the axis is current, and here is the voltage. And any variation in the voltage that you see here, it can be monitored as a variation in the current. Yeah. So this is what we are using. So how do we fabricate these sensors? So again, it's just very conceptual. So we do thin film fabrication. This is on the wafer scale. We start by what we call CVD graphene. These sensors are, the CVD graphene then is transferred into a clean room technology at wafer scale. We are going to work on, the wafer silicon, but we use flexible polymer on the surface of the silicon. So in this case, it's polyimide, and then you can fabricate like a flexible sensor. Yeah. So this is an example of the technologies, or the most advanced technology that we have. This is an array of 1,000 sensors on a 6 by 6 millimeter. This is a probe that which is used. I'm going to show for monitoring rodents, and you can see the type of sensor that we can have. At the end, you have a resolution in our case of sensors of 20 times 20 micrometer up to 100 times 100 micrometer. Yeah, so this is the typical type of sensor array of sensors that we can fabricate. This is for monitoring just the activity on the surface of the brain. I mentioned that sometimes you want to go deep inside the brain because you want to reach areas that are not on the surface. You can do cortical recordings, you can do subcortical recordings. So you can do exactly the same. You can fabricate devices which are still flexible. This is all flexible, but you can rigidify temporarily. During the insert, you can insert it, and then the device becomes flexible again. So there are different ways to use some polymer and hydrogels that are rigid when they are in the dry conditions, and they become or they dissolved once that they are in a wet environment. Yeah, you can control the time that they need to dissolve. Yeah, so this is the same technology, but instead of on the surface going deep. Yeah, so let me show a couple of slides on the characterization of the technology, and then I go to some of the neural recordings. So this is an example of an array of 16 times 16, 256 sensors, and you can see here the curves, all of the sensors within one array. Certainly, we are in a research environment still, and there is some dispersion in the curves, and this is the gray area that you see here. The top right curve shows a map of the gain of each of the transistors. Yeah, and you can see that there is a variation. Yeah, and that's something that we need to deal with. And here on the bottom left, you can see the same variation of the gain for different devices, just to show homogeneity or reproducibility. And you can see that in terms of yield, the devices are not so bad. So 256 sensors working, 252, 253. So in terms of yield, we are not too bad. We are worse in terms of dispersion. Yeah, and I'm going to, and this means that you need to consider the gain of each sensor when you want to for the recordings. No, let me just go a bit quicker. So when we started to do this work, then we developed the sensors, and then you said you need to think, how can I measure these sensors, right? There are no commercial devices to measure from this type of technology because we are developing the technology. So we needed to develop also the electronics to read at the very same time for the sensor. Commercial, I mean, in the field of electrophysiology, all the available devices are based on recording from electrodes and not for transistors, and we are using transistors. So here we needed to develop a system that basically this is your device, and we have an electronic that basically separate the signal, and you will see why, between low frequency signals, what we call DC signals, and the high frequency signals. We amplify them at a different level, and then we can have access to both the low frequency and the high frequency. Whereas when you use a passive sensor, you only have access to the high frequency. Anyway, this has been developed into an ASIC, not only into like a discrete technology, but also integrated technology together with colleagues at the microelectronics centers in Barcelona, but also with a German company, which are leaders in electrophysiology for preclinical research. It's called multi-channel systems. So you can see here the type of ASIC that has been developed. This ASIC is integrated into a PCB with an FPGA, that everything is on the head stage that can be implanted for doing some recordings. Yeah. Okay, so just want to mention about multiplexing strategies. I'm not going to show how we do it exactly. I just want to mention, because it's very interesting, that there are two ways that you can do this multiplexing that I've been mentioning before. You can do what is called the time domain multiplexing, in which you have an array and you switch between transistors in time, one after the other, one column after the other, right? That switch, it's a bit, it generates artifacts. You are switching very fast, no? And you are also reading fast. There is another way to do it, which is, and we had a patent of that, which is very useful. It's in the frequency domain. So you can operate all the columns at different frequencies, yeah? And then I'm recording from all the devices at the very same time, but the recordings of each column is happening in a different frequency, right? I'm just shifting the frequencies while measuring, it's like a lock-in operation. So I'm just shifting the frequency base to different regimes, no? And that's very useful because there are no artifacts, no? And it's a very interesting way of recording. Okay, so I'm going to show you some of the capabilities in terms of recordings for those of you who are doing electrophysiology. So this is an example of what we call the wide bandwidth recording capabilities of the active sensor. This is a recording of this is an intracortical device that goes across the cortex. So there are, this is non-multiplex. I'll show multiplex later on, but there are 16 devices here at recording from different layers in the cortex. And this is an example of the recordings, two channels, the two lines on the top and the two lines in the bottom. Each of them correspond to two different channels. The color code, the black, corresponds to what we call the full bandwidth, including the infraslow activity, and the red color correspond to the standard AC recordings that you can use with passive electrodes. And you can see that, the interesting thing here for those who are experts in the field is like, you can, of course, record over hours without any drift in the recordings. And this is very, very important. Typically, when you do recordings over hours with your with passive electrodes, you need to reset continuously some of the, if you're measuring low frequency, you need to reset continuously the amplifier because of drifts. But you can record without hours, without any drift. You can record precisely baselines, standard activity like theta bands, seizure type of activity with a very high precision. No, so one of the things that it is most useful and why there is most interest in this technology, at least with colleagues doing neuroscience, it's in the capability to record infraslow activity, very low frequencies. Yeah, this is called it's called infraslow activity which is below 0.1 hertz. These are the recordings from this array of sensors, which is intracortical. Each of them correspond to one of the sensors. And if you take a look here to the scale, for those of you who are expert in the field, this is 50 seconds. This is a very, very long, extremely slow activity. And these are 10 millivolts, the scale. No? So we see that there are extremely large and very slow signals which are happening in the brain, and typically it's very difficult to record them with passive electrodes. So, for instance, just as an example, the top curve corresponds to this activity, which is recorded with active electrodes, which is the infraslow activity, whereas the blue one corresponds to what you would see with just with a standard passive electrode. So both, the red one shows exactly the same signal that the blue one, but on top of that, is able to record this very slow activity. And this very slow activity is very important. Why? Because in this particular case, which is a epileptic seizure, there is what we call a DC shift. This is a very slow change in the potential that precedes the seizure happening. So you will see that eventually we could use these very low signals in order to monitor brain activity and deliver a therapy before the seizure it's really happening or invading the whole tissue. Yeah. Okay. So far I didn't show yet I didn't show any large scale high density multiplexing. I'm going to show this now. So the typical devices that we have are for small animals. So these are designed for rats, which would cover both. We are interested in covering both hemispheres at the very same time, the complete both hemispheres with 1,000 sensors. And also in our way, I'll show at the very end of the presentation, scaling towards human. We are also scaling in for large animals. In this case, are for pigs or mini pigs, or devices that have been used in pigs or mini pigs. So this is a video showing the power of these high density arrays. So this is an array of, in this case, only 256, covering both hemisphere in a rat. This is what you see here is the power in the local field potential regime from 1 to 40 hertz, and the bottom graph shows the same recordings but in a different frequency, the infraslow activity. That is the one that we can record also with our transistors. No, and this is just to show the richness of the topography that you can obtain when you have high density recordings, and this is done in a awake animal that has also these electronics, integrated electronics. No, why this is interesting? I mentioned for some applications, for instance, you have patients with locked-in syndrome or aphasia, patients that cannot communicate at all. There are several groups worldwide developing brain-computer interfaces for speech prosthesis, right? Some of these patients need communication, and a solution for that would be to have a BCI, brain-computer interface, that would monitor brain activity in the speech, related to speech, to language. And this is an area which is broadly distributed in the brain. It's not just one single area as it's shown here, right? There are different regions that are marked in color that we know that are activated when the patients intend to speak, or when we humans are speaking, right? So the idea here is to cover some of this area, which you can see that as a large area, with these devices, in order to provide or to offer a proper decoding to understand what are the words that the patients want to speak. There are already demonstrators of this technology coming from a couple of groups in Harvard. No, why this is of interest? I just want to, if you would, the technology that we are using now. I see. Sorry. Let's put it. The two videos, they are exactly the same video. Yeah. The left one is the high density that I'm telling you, and the one on the right-hand side, it's the highest density that you have normally now in clinical devices. Yeah, and you can see how difficult it's going to do a proper decoding with this type of resolution that we have now, compared to the decoding that you can have with novel technologies. Okay, so I want to move to the second part, which is about therapy delivery, stimulation. With all the beautiful things that I show about the transistors, unfortunately, they cannot stimulate. Yeah? Nothing is perfect. We cannot use these active devices for stimulating brain tissue. And we are interested in stimulating brain tissue. Delivering therapy means introducing stimulation. Yeah. So how can we use stimulation? The first thing is like, what is the challenge? No, why stimulation is relevant, and why focal stimulation is relevant. What I'm saying is like, in order to advance the current clinical available devices, we need to reduce the dimensions of the electrodes. They have the electrodes which are of the order of 5 to 10 millimeter in diameter, that are spaced by 1 centimeter. Yeah? So that the type of resolution that you get there is very poor. So where do you need resolution? I'm going just to give you an example. I'll show a couple of examples. Like experiments with this. One example could be retinal implants. Patients with degeneration of the photoreceptors. There are patients implanted with devices, microelectrode arrays that are either subretinal or epiretinal implanted. And you don't have the action potential generated by the photoreceptors, but you can take an external image, a camera, convert it into a train on electric impulses that are sent to a microelectrode array that is implanted in the retina, and you can aim at generating the visual perception in the patient. And I'm saying aim to generate visual perception. I'm saying that because we are not there yet. We are not able to restore full vision. But now current patients, not we in general, the scientific community, they can see, they recover part of their vision, they can see large letters, and they can navigate their space. Yeah. But here, precision is very important. So if you would think of having like a optical image, and you can offer your patients stimulation from 100 channels, which is the maximum that we have now in the clinic, you can understand that the patients cannot gain visual acuity because you have a pixelated image of your space. No? So you need to move towards thousands of electrodes that can stimulate in order to dream of offering like a full restoration of vision. But if you think in the area of your retina, and you think which is a few millimeters, and you think thousands of stimulators in there, it's obviously very clear that you need to go to sizes which are below 100 micrometers in diameter. And I'm saying that the materials that are typically used in the clinic, like platinum, iridium, they cannot be miniaturized at that size and still deliver the current that is needed. We need other materials, no? And there is where graphene was of interest. We started with the CVD graphene that I shown before, and we soon realized that, well, that was not going to work. CVD graphene I didn't mention, but we are using one single layer. It's single layer graphene, one atom thick layer of carbon films, and that's not sufficient. There is not sufficient density of states, electrons there in order to deliver sufficient charge. So what we started to do is what others in other fields are doing. In order to improve the charge stimulation capacity of materials, people or researchers are going from flat devices towards porous devices. Yeah, if you think of this is the same that you have supercapacitor, no? Initially, supercapacitors were thinking like a flat devices, but if you want to increase the density of charge that you can store, you need to go 3 dimensions. You need to do a porous material, and this is where we take advantage of graphene and other 2D materials that can be assembled thanks to the van der Waals interaction between these materials. Yeah. So what we are building, it's not the slide correct, but anyway, what we start from a solution of flakes of graphene that you can assemble in a special way, one on top of the other, until you form a layer of film, which is highly porous. And we have pores here that are of the order of 1 to 2 nanometer, right? So, and this is thanks to the stacking that you can get between this layer. The beauty of that is that you can integrate that in the same flexible type of technology that I have shown before, right? I can fabricate that type of a membrane of graphene and then transfer to my wafer and do all the steps in semiconductor technology that we have learned before, and you can fabricate the same type of devices. So this is just an example of the type of devices that we can fabricate. Each of these dots here is one of the graphene, what we call reduced graphene oxide electrodes, 25 micrometer, very small electrodes that have 3 dimensions. Yeah, they are porous. Each of them is 25 micrometer in diameter, but it has 1 or 1.5 micrometer in thickness, right? And everything is full with very small pores, which allows you to introduce a lot of charge. Okay, so let me just go to some of the examples of the that we have done. So we initially started with the simple thing, which is, okay, you try to demonstrate whether your capabilities are good. You don't go directly to humans. You need to go step by step. You start with cell cultures, and this is a typical device that we use. You can have in a rigid or not rigid, but like what we call a microelectrode array, an array where you can cultivate cells or where you can bring like tissue on the surface in order to do electrophysiology. So this is a device that you can see here. Each of these dots, it's where the graphene is, no, and then the other are the metal lines, which everything is covered, no, and you can put this in cell cultures. And this is just an example to show that you can stimulate with the electrodes, and you can do the recordings with the rest of your electrodes. So your devices can do stimulation, can stimulate, and each of these the recordings that you see here are recordings that are triggered or invoked because of the activity that you generate in some of the other electrodes. Why this is interesting? Okay, this is just to show the quality of the individual cells recordings that you can have. No, as I told you, you need to record signals which are 50, 100 microvolts at most. No, and the time resolution needs to be below 0.1 millisecond. So I'm going to show later on some applications in the field of retinal implants. So the next step was, okay, let's take not normal cells, let's take an explanted retina. Yeah, we are interested in delivering therapy for patients, but we need to understand first what type of capabilities we have in delivering that therapy, what type of current we can inject, what type of capabilities for recording. And what we do is like you can explant a retina. This is a retinal explanted from an animal. You can put it on the array that I have shown before, this type of array, and you can see here the retina with on top of the array. And now what you can do is you can take electrical stimulation, and then you can change that electrical stimulation paradigm. I can change the frequency, I can change the amplitude, I can change the time of the pulses in order to develop the therapy that I want, in order to understand how focal I can be. And that the picture on the right-hand side is just a fluorescence image. Well, it's not working now, but it's showing that when you apply your this is a stimulating electrode. When I was stimulating the electrode, you could see that some of the cells were being active. No, this is calcium, just calcium imaging. And in that way, what we are trying to understand is like how focal is the stimulation that I'm introducing, and how I can change that focality by changing the parameters of the stimulation, frequency and amplitude. You can do that with the image that I have shown before, the calcium imaging, or you can, since my other electrodes can also record, I can record from the other electrodes and see what they see. And this is an example of experiment in which you apply an impulse, electrical impulse with one of the electrodes, and you record from the others. And this is what the others see. And you can see the spikes which appear right after the stimulation. And I can do this for different currents. You can see for 40 microamps, 30 microamps, 20, no? And then I can measure each of the spikes. This is each of the dots is one spike, right? And I can build curves which are like that, right? The firing probability as a function of the current. And this is a way to tune, or the way to adjust the therapy that I won't be delivering in the animal in the next phase, no? Okay, so now we went to the animal, and this is the type of implant that you can do. This is a very complex surgery. This is done in collaboration with the Paris Vision Institute, and they have excellent surgeons in order to implant in a rat this type of device. This device is implanted on the retina. We had electrodes with different size. We wanted to understand what is the impact on the size, on the stimulation capabilities. And what I'm going to show, all the experiments, but what I'm going to show is like how we try to monitor what the animal could be seeing. Yeah, that's complex. What we are going to do is we are going to use a technique which is called focus ultrasound probe. And what you're going to monitor there is like a blood flow, right? We know that blood flow is related to activity in the brain. And focus ultrasound is a very useful technique. It's a very new technique in order to monitor that. Yeah, because you can go in depth, right? Without the need of, and this can be without the need of opening the skull. And we're going to be monitoring different regions. So this is a cross section of the brain, and we're going to be monitoring the activity that the retinal stimulation that we do generates in different areas of the visual path, the superior colliculus or the visual cortex. Yeah, so we are going to be stimulating with some of the electrodes, and we are going to be monitoring. So the first thing is like, okay, let's see what the animal sees when we stimulate with light. No, this is a non-diseased animal. Yeah, it's a non-blind animal. And this is the typical image that you obtain. The animal stimulated with a LED. It has both stimulating in both eyes, and that's why also we see activity in both in the regions here with the superior colliculus. Yeah, and here you show this is the image of the ultrasound. The black curve is the ultrasound, and the red is when we illuminate with the light, and you can see how the increases the activity, no, once you stimulate, or just only during the stimulation. And now we take our electrical stimulation, right? And we try to define, okay, what are the best parameters to induce a pattern which is similar, right? So with electrical stimulation, you also obtain activity in the superior colliculus. Very interesting. You only obtaining one of them because it's stimulating just one retina, not the other. And at the moment, what we can obtain is what we're trying to optimize is what type of stimulation we need to do in order to get closer and closer to the standard pattern that you would see. Yeah. So this is one example of the why you need focality, you know, when you stimulate. The other example I want to show very quickly is in the area of spinal cord stimulation or patients with paralysis, paraplegia, for instance. If you think of a concept in which I have a sciatic nerve, and I would like to stimulate the sciatic nerve and understand how that stimulation impacts on the muscles, right? The sciatic nerve is the one that innervates the muscles, and the different fascicles within the sciatic nerve are going to be in charge of controlling these different muscles. You know? So if you want to induce muscle activity in just a muscle and not the other, you need to make sure that you have precision and spatial resolution to activate just some fiber. And again, here you need very small electrodes. You cannot use the large electrodes that we have in the clinic. They are too large. And then, so the example here is like, the experiment is like, we're going to introduce a very small electrode array, and we're going to stimulate each of the electrodes and record from the different muscle to understand the selectivity concept, no? So this is the type of electrode array that we have. There are 19 electrodes, 9 on one side, 9 on the other side, and they crossing the 1 millimeter of a sciatic nerve. Yeah, this is in rodents. And the typical experiment is just goes like this. I'm not going to go to detail, but you increase the current stimulation, and we are measuring in the muscle electromyography for either different muscle, no, the tibialis anterior, no, the plantar, yeah. And you see, this is the activity that you can measure in each of the muscle, and you can have a plot that looks like that. I increasing the current, and what I'm obtaining for each of the 9 electrodes at different amplitudes in different muscle, no? These are comparing to different muscle. Let's say when I'm monitoring the tibialis anterior, electrode, let's say A1, tells me that that electrode, when I stimulate that electrode, this muscle react very well. This is the amplitude, the maximum amplitude of reaction. Yeah. However, if I stimulate with electrode 9, which probably is far away from the fascicle, I cannot obtain that activation. However, A9 works very well for another muscle, whereas, for instance, let's say A5 doesn't work well. No, so that allows you to build a plot which is like here, which is a selectivity plot. No, it's just a plot in which you say, okay, what is the maximum response that I can obtain for certain current, and I could then select which current and which electrode, and allows me to generate activity in each of the muscles. Okay, so I'm going to conclude by just saying a couple of things of clinical translation and some of the challenges. I mean, what I've shown before, it's only animal work, yeah, and it has a lot of value for neuroscientists and also for clinicians who try to understand and how to improve the therapies. So there are two applications of the technology that we develop. One is in the preclinical neuroscience, collaborations with colleagues. Some of you might be interested in getting access to this technology, to these devices, in order to do basic research. But of course, it also has, and hopefully has, and that's why we're dedicating our lives to that, it has an impact in the medical field. Yeah, unfortunately, these are two different fields in terms of challenges. No, what I mean, the neuroscience field would be like what we call a low-hanging fruit for this application. There's almost no regulation. There is no adoption, or the market entry is very simple. You don't need to convince clinicians. The researchers are always convinced of using new technology. No. However, if you want to go towards the more juicy from the financial point of view and from the impact in society, this is what we call high-hanging fruit, right? Regulatory approval is extremely complex. Clinical acceptance is very difficult, and research organizations don't have the means to do it. No, we were saying before that we realized that if we want to bring this technology to humans, we cannot do it in our institution, in our research institution. Yeah. So now we needed to think of a vehicle, that would allow to do that, and this is why we created a company, an industry. We realized that without that company, without the focus that you have in a company, without the resources that you are able to attract with a company, in contrast to a research organization, you will not succeed. No, so in fact, we transfer the technology, the preclinical device technology, to multi-channel system, and the technology was also transferred to this vehicle that we created, which is called In-Brain Neuroelectronics, which is a company which is developing neuroelectronic therapies for the treatment of neurological disorders, so brain disorders in general. Yeah. So this is a spin-off from the ICN2, but it's also a spin-off from ICREA and from other organizations that are supporting this project. No. So where we are in this company. So the first thing is to understand that you are trying to change some of the ways that the clinicians are using, or the tools the clinicians are using to monitor brain activity, and the design, and the materials. And the problem is that your material that you're using is graphene, which is also a nanomaterial. So, I mean, all the bells start ringing, all the alarms are in terms of regulatory. Right? This is a very complex, no? So now we thought, okay, how is the best way to reach the clinic, the fastest way to reach the clinic, to demonstrate that these devices are safe, because the first thing that you need to prove that they are going to be safe. And this is a clinical trial that is in progress, the preparation. So we thought, okay, what we need to do is not to keep a device implanted in a human for a long time, because there you need to demonstrate safety for a long time. Yeah, but you could use a paradigm where implantation is not needed. For instance, this intraoperative monitoring during brain surgery, the patient is going to be there's going to be a craniotomy. The patient is going to go through a resection process, and the clinicians, they're already using some similar device, equivalent devices to monitor brain activity. They put the device, they monitor, and they remove it after 1 hour or something like that. So we are going to do the same. This is a project, or this clinical trial is financed by the Graphene flagship, and it's going to be happening at the Manchester former Salford Royal Hospital, which is a referral center for brain surgery in the UK. And this is one of the type of devices that we are going to be using. And the goal of this clinical trial is basically demonstrating mostly safety and functionality, that your electrodes do what you promise to do. They can record, and that they improve the and the capabilities of current technology. So the study is quite advanced. We have demonstrated, we've gone through all the pain of regulatory and standardization and for preparing a medical device. As I said, we couldn't do that effort in our organization. So we had done GLP, so good lab practice studies with large animals in the very same conditions that you're going to do this with the neurosurgeons. And this is just the same device that are going to be used in humans. And this is just an example of what we are monitoring there. So we were trying to we are trying to map or to demonstrate that we can map with high precision the different regions, and we can decode the different regions associated, for instance, to different parts of the patient. In the case of this experiment here, it was the tongue. So we were stimulating the tongue, and we were monitoring in the cortex and sensory area. We were monitoring the activity as to define where is the tongue map, and then as like an example of, well, I wouldn't like to touch that part if I'm going to do a resection. Okay, so just to finish, as we said, I want to finish with 2 slides, like saying, okay, I talked to you about the medical need. I told you that there are non-medical needs, and it happens that the funding, the driving force in the field is over there. Yeah. On the other hand, I told you that the technologies which are commercially available, they look like that. They are very simple devices, 4 electrodes, 16 electrodes, 64 electrodes. So we are still very far away from that dream or some promise that some of these companies are doing. But when I think of, when you look at the 9,000, I mean, in the last century, 60 years later, we went from first flight to the moon. I mean, it's impressive. And you see how things are changing quickly. No? So I think that is very important that there is a strong, well, there is at least a discussion at the societal level, how brain-computer interfaces need to have some regulation, the same way that yesterday the European Commission passed a law on artificial intelligence to regulate how we can use artificial intelligence. The same thing needs to be applied here. We need to understand whether and how we are going to apply brain-computer interfaces, because at the end, you could think that eventually they could monitor some of our brain activity, which is what we are. No, it's our inner part. And at the moment, there is no regulation for this. So with this, I just want to thank the collaborators. I mean, this is by no means the work of one team. Yeah, we are very multidisciplinary. We have many collaborators, both in technology, in neuroscience, that are supporting us, and there are plenty of funding agencies who are helping us. And thank you very much for your attention.
¿Funciona? Ahora sí, sí, muy bien. Bueno, that was fantastic. That was so interesting. I think it's quite rare for me to learn so much in a 45-minute chat.
Sorry.
I have a lot of questions to ask you. I will pass over to my colleagues first, I think. Well, maybe just one quick one. So I'm having a clinical background, seeing the rigid electrodes when they go in, they're covered with you said a polymer that when they get wet, they get more flexible.
Yeah.
So what happens to the polymer? It must go somewhere.
Oh yeah.
Yeah.
It's a biopolymer, and we've been checking that it's that is degraded in the form that it is in the tissue. So there are studies with histology that there is not a major impact, at least on the time that we are looking at it. for animal experiments, that's feasible. I don't think that this will be used in humans.
You don't think?
At least not on the short term. No, I think that there are other ways, we were commenting, there are other ways of doing like a deployment of these devices, through robotic implantation that cannot be used in the small animals. I mean, the small animal, everything, I mean, the brain is so small that applying any technology for robotic implantation, I mean, you need to go to nano robots, not to millimeter type of robots, but in the human brain, you can use other type of approaches.
And just one other thing. So when you show the slide of the medical devices, so the deep brain stimulation electrodes, I mean, they haven't changed very much in 10 years or 12 years that I've been doing this.
In 20 years.
Yeah, in 20 years. So that's, so to see how that's going to suddenly take off will be interesting to see how that can happen.
Yeah.
I mean, one question for you. So the electrodes that I've used, in the patients that I've studied, they only stimulate.
Yeah.
So you can, in the post-operative period before the wires get tunneled to the generator, you can record from them. But then, what's the next step for these electrodes to be read and write?
Yeah.
What do you think needs to happen?
It's a pity I didn't put this. I mean, I showed that for the retina case that you can do read and stimulation. And so I have I can show you later. We have devices that in deep brain stimulation, you can do recording and stimulation at the very same time. You can see for closed loop. This is very important. And the current deep brain stimulation devices, they mostly do open loop, which means that the neurologists adjust the stimulation, right? And off goes the patient, and then maybe it requires like a adjustment. And it depends, I mean, independently of whether the patient is sleeping or not sleeping. And there is the concept of closed loop, that what you want to do is you want to adapt stimulation, but you need some biomarkers. So what you want to do is to read brain activity, and the system decides what type of therapy is going to do. I can show you definitely the new generation that we are developing, and that this is part of InBrain, the core of InBrain. It's a lead with recording and stimulation electrodes at the very same time.
Yes. Right. Anyone else have a question? I'm sure there's.
I have several questions. In the muscular stimulation, you show the signals, the muscular response. In the second case, there is kind of delay, right? The GM.
Yeah.
So you have a much better response for the 8.7 and 8.8 electrode.
Yeah.
But the 1, 2, 3, 4 also have a show a good one, but later.
Yeah.
So is that delay related with distance from the electrode to the muscle?
Yeah. It's from distance of the electrode to the nerve. I mean, I didn't explain this, so I apologize. So what you see, I mean, is delay, but the time there is because the experiment increases over time the current. So imagine I have a pulse, that it's in which the amplitude of the pulse is increasing with time. Yeah. So it means that at this time I'm applying that current. So the currents that I'm applying is different each time. It's just to extract information. So what's happening is like as you said, at this time, for instance, because I have a large current, I manage with this electrode to collect to activate all the fibers of the muscle. Whereas with the other electrode, since that electrode is far away from the nerve, from the fascicle, which innervates that nerve. Imagine I'm here or I'm here. If I'm interested just in this fascicle, with one electrode, I need certain current, and with this electrode, eventually, if I put sufficient current, I will be able to activate also that fascicle.
So it works like a threshold, right?
Sorry?
It works like a threshold.
Exactly. It is, and I didn't explain that again, so it's my fault. Here is the threshold that you see. Let's say this is the maximum current, the maximum response of the muscle, yeah, as a function of the current. Let's say that I take A7. Imagine that with A7 I apply 40 microns. With A7 I can obtain the maximum response of this muscle, but I have minimum response of that. It's not perfect, no, because the selectivity is not perfect yet there, but it gives you that some sort of threshold of which current I can use and which electrode to obtain muscle response.
Beautiful. Now, in the rat stimulation, where you have the matrix of dots, and you show the video of the activity. Remember the orange one? At the beginning, almost the beginning, back before that one is a interspike distribution, right? This is a
histogram. Sorry, this is a histogram again showing spikes.
But interspike, right? Bit distant.
No, it is in time. So each of these dots corresponds to a.
But the other one.
This is the same. How many spikes I have? This is counting how many spikes I have at a certain time. So that you see that I stimulate, and this cell, because this is an individual cell, is spiking mostly at the beginning, and suddenly it becomes silent. I would need to have another spike. I need to stimulate again in order to generate again this train of spikes. And these are individual cells, no? And it's very interesting because you see how each of them is a trial. So I do a trial and I get the activity, which is, you see that they have a spike. I do another trial, spike. And it's perfectly on time. And this is because you can do recording and stimulation at the same time. And we showed this also in the DBS, but I didn't.
So in the previous video, the one of the matrix of electrodes, no, the one before.
Was there any before?
Before.
You mean on the recording?
Yes, that one.
This one?
This one, the top one.
Yeah.
Have you analyzed that pattern of activity? That's a frequency content, right?
That's power integrated between 1 and 40 hertz.
Okay.
And you can, there's a nice paper that is going to be published on the deep analysis. It's just to show, it's just to give an impression. It's more marketing, like it's showing with high resolution. Of course, you have information, and with low resolution, you are missing so much that decoding is very complex, no?
So there is an hypothesis of turbulence in the brain activity, right?
Of
turbulence.
Oscillations or
turbulence, pure turbulence.
Okay, no.
And when I see that, I see turbulence there.
Okay, well,
So I want that paper.
Okay.
Thank you. Thank you very much.
Yeah.
Beautiful work.
Thank you.
Thank you. Just one point that for those that don't work in human neuroscience that much. So there is a signal in the human brain. It's also in the mammalian brain, which is very slow. And it's what you see in resting state networks. So it's between really around 0.01 hertz, so one oscillation every 100 seconds. So the one thing that it's going towards is that we don't have ways to record this electrophysiology very well. So we record it with functional MRI. This sort of recording at that sort of scale, when you see 0.01, you see, okay, so there's a technique that we can work out, because we have this resting state signal in fMRI that we don't understand. We don't know why it's there or where it comes from.
Yeah.
Another question.
Hi, congratulations for your presentation.
Thank you.
It was excellent. I just have a few questions. The first is, I understand that you will be the first to use graphene in neuromodulation. So will this device—
in humans, not in animals, yeah?
So will this device have advantages for those patients who have to undergo MRI or CT scans, for example, or could be a limitation considering the type of material. And the other thing is, given the advantages of graphene and in terms of flexibility and resistance, could this system be more cost effective for patients with neurodegenerative diseases compared to other or the current technologies, or perhaps could be more expensive due to the type of material? And thank you.
Yeah. So the first one, I mean, in terms of CT or MRI, principal graphene is transparent there. So, but I mean, the devices are not just graphene. Yeah, graphene. And if you look at one of these devices, there are so many metals or the materials. No, graphene is a small area of the device. No, so when you think of compatibility, CT or MRI, it needs to be compatibility of the whole system. Yeah, and therefore this is where we work. No, I mean, graphene does not bring any additional issue. It's transparent to CT and to MRI, so that's fine. In that respect, it's not like you would use another metal that would generate an MRI artifact, right? So that's fine. Actually, in the case of CT, it's even transparent, so it's not so good because you want to see it sometimes, no? But in that respect, it's fine. I mean, with respect to cost, I mean, cost is complex, no? Because it helps. I mean, it depends a lot on the volume that you can know, and how many other companies are developing the technology that reduces the cost initially. And for a company, you cannot go with a higher cost than what is in the market. This will not work. So the goal of these companies is to go to the market with the same price at least, but offering advanced our advantages. Some of the advantages that I'm not showing here that has to do with the closed loop concept is like you could reduce dramatically the use of power. The current system, they just do open loop, they stimulate continuously, and they don't care if the patient is sleeping or is not sleeping or no. And we know that these consume a large amount of the battery, and it needs a large battery. So if you can reduce very much the battery usage or the power use, because you can select when you want to stimulate or regulate the stimulation. And it's not the same if the patient is going to. It was a fantastic video in a movement disorder conference of a guitarist, electric guitar player, and he wanted to have different modes of stimulation. When he was going to do playing guitar, he wanted to make sure that he had no tremor, and he was not so concerned with having a bit more tremor in the different conditions. No, so adjusting is very important, and you can reduce battery size. So I think that there are other advantages beyond the cost. The cost at the end is like how many devices you can sell at the end, no? Because then you can reduce the cost of production.
That's very, very interesting points. I mean, localizing electrodes in humans is not as trivial, not as trivial as it sounds. So my group will tell you, or I'm not laughing because we're working on the same thing. The point another point to raise with the closed loop stimulation is that in a condition like Parkinson's, where you have what is a dysrhythmia in the targets, you have the beta oscillation in the subthalamic nucleus. At the same time as closed loop is being developed, we're also looking for biomarkers for other conditions where it's not very clear. So in the psychiatric diseases that we use deep brain stimulation. So what is the biomarker? When are we going to when is the closed loop system going to be able to come into play? So we may actually need more recording devices throughout the brain and the stimulation device.
Yeah, of course. Our goal is to combine the two concepts that I show. We have cortical recordings, right, and deep recordings. I mean, the brain is not just it's not nuclei. It's not just one nuclei which is independent of the motor cortex. In the case of Parkinson, no, we know that it's a network, no, and that network is the one that oscillates wrongly. So you can monitor in some region, you can stimulate in a different one, no, and yes, having the capability to record gives you the biomarker, not the capability to decide what is the right biomarker, because we don't know it. properly. No, there are some hypotheses of what is the right biomarker that you can use to do closed loop, but it's not there yet. And one of the reasons is that we don't have sufficient recoding capabilities.
Absolutely. We have some questions online.
Yes, we do.
Do you want to read them out?
There is one from Guillermo de Arcas. He's a professor from the UPN. I don't know if you know him. He said, thanks for the brilliant presentation and sorry that I could not be there today in person. And then you have focused mainly on internal electrodes, but could this technology be used to improve external electrodes, for example, for dry EEGs?
Yeah, we were talking about with Brian a moment before that. I mean, we're thinking about that. I mean, it's a very interesting. Thanks for the question. I think that is very interesting also from the perspective of broadly use and adoption. No, it's not the same to develop a technology that is invasive than a technology that you just put on your skin. No, so from the regulatory perspective, it's so different. What I think is like two ways of answering this question. One is I personally think that the advantage of using graphene is much lower when you go outside, and one of the reasons is that when you go outside, you just lose resolution, right? In the sense that when you are on the skull, you have the skin, you have the skull, the bone, tissue. You lose a lot of spatial resolution. So having a small electrode is not a large advantage. So I think that there is a more advantage when you are inside, when you're close to the tissue, where you can have very small electrodes, where you need precision and spatial resolution. I mean, having said that, it is true that if you can improve the properties of the dry electrodes that we have now in EEG, that would be very useful. Yet we have explored it, and we have not found that killer application, no, the key advantage with respect to the dry EEG that they use silver chloride. No.
Thank you. More questions? That's what there was. Yeah.
Thank you for your talk, José Antonio. I was wondering if when you move from the 2D material for sensing applications and you go towards acting applications, no, where you are using this 3D graphene graphene oxide, no, reduced. Are you losing some information that you can do in high frequency domain? Like how? Because I don't know anything regarding how to do that.
I mean, what we lose is when you go from the CVD graphene, the active sensor, to the stimulator, what you lose is the infraslow activity. So with passive electrodes, whatever they are based on graphene or on metal electrodes, measuring activity at very low frequencies is very complex. So we know that we lose that part of the infraslow activity, below, and also the rest of the neural network. So below 0.1 hertz is very difficult to measure. But high frequency, there is no problem. We can measure without problem towards a very high frequency. And it's also because high frequency in this case is 1 kilohertz. Yeah. So it's not like maybe the high frequency that you have in mind for CVD graphene that you need to go to megahertz. No, we don't need in biology. If we measure till 10 kilohertz, we are happy with that. No? So we don't lose in high frequency, we lose in low frequency.
Yeah, so I was more thinking on, like, you have the retina, no, and you have the cell, how fast you can drive that cell, no? And if you said that 1 kilohertz, that's fast enough, I guess.
Yeah, exactly. So it also in stimulation, I mean, I didn't show it, but for instance, we do typical stimulation pulses in deep brain stimulation can go to 90 microseconds. So we do pulses of 100 microseconds to stimulate the tissue, and this is no problem.
Okay, thank you.
Vivos.
Which are the patterns simulation of directing your experiments?
The patterns? we use bipolar, no biphasic stimulation. This, you mean what type of stimulation we apply right now, or? Oh. Yeah. And what we do at the moment we are not connecting with the external world. At the moment, what we are doing is like we have an array. And what we are trying to understand is like if we can stimulate this array with, let's say, one sensor, multiple sensors, a bar, a square. Exactly. If we can, this is where we are now. We are doing this right. So try to see whether when we do pattern stimulation, we can monitor a pattern on the circuit. But the parameter space is huge because you can stimulate, as I said, bipolar, monopolar. You can use. There are some work showing that if you stimulate just one by one, or if you move you move your stimulation, the impact is very different. No? So we are just exploring all the parameter space, the delay between the pulses and so on. We don't have this space well explored.
And I think just maybe one point to finish off on a more general question here. I mean, you raised this very good point that the money goes to the hype, right? Mm-hmm. The investment is going to the hype that I'm going to read your mind, and then we can drive our cars using just our brain waves. So what should we do to put the money where the real progress is going to be made? Any ideas? And I can maybe also ask Guillermo Velasco, who is the university expert in tech transfer and innovation, for a comment, perhaps.
Well, I mean, I don't think that the money just go there. I think that there are positive aspects of having that hype around, because it's I think that it triggers the ecosystem. It boosts a bit the ecosystem. So there's money going there, but there's money going into the real medical application. The second thing is, even in some of these companies, they've gone through the learning, them and their investors, that working in a heavily regulated environment like medical devices, you cannot just say, okay, I'm going just to do a study in 1,000 humans because I want them to drive a car. No, then the regulator is going to tell you, sorry, this is not possible, no, because we need to do studies with patients, right? So you need to prove what is the advantage for your patient. So most of them, they realize that they need to change even the focus of the company, and in order to demonstrate to the regulator that they are going to have, or that they have a concept to help patients. So maybe this regulated environment where we are, it's sort of like a redirect some of the intentions of the company. Of course, is different is what once that they develop this for a patient and what they do with the technology, because it's clearly, I mean, if you think in terms of money, if you think of just Parkinson's disease, right? How many patients in the how many patients in the we have in population with Parkinson's disease? It's large, but there are 300,000 worldwide implanted. And some of these companies, what they want to have is that every person has an implant. So the market is so different.
We bankrupt the health system. Yeah. Guillermo, do you want to say something?
Well, thank you for this presentation. Well, regarding Brian's suggestion, we have, for example, many and very recent examples of what the investors want to put money in at least in the human brain project context where we work. Very recently, we had a bootcamp for investors where different startups emerging from the project have shown this kind of breakthrough and radical innovations. And what my learning from these investors feedback is that they are really interested in the impact, and social, not only the economic impact, but the social impact behind the solutions. So that is brain disorders oriented solutions are the ones that they like better to put money on. This kind of more hype solutions that are more sensationalist things that are happening and we can read and watch everywhere, every day around, are not likely, in my opinion, are not are ambitions and are things that are not really in the background of these investors companies. So my understanding of this interaction that we have this capital institutions, actors, is that they are really interested in practical things, the regulatory devices problems that they need to overcome is obviously a barrier that needs to be considered when you want to put money. But in any case, I think that this kind of solutions that impact directly to the society is what they look for. So this we have a very recent experience of that, very in Brussels last.
It could be also like a cultural. I can tell you that it's not the same European investors than American investors or Asian investors. So I think that the feedback that you might have from Asian investors, it would be very different. No? So, and also whether you talk to medtech investors who are very knowledgeable on regulatory barriers and the hurdles to go, or if you talk to deep tech investors, no, that have no idea about regulation and they don't care, in the sense that it's not in the background, they just want to push towards like a large number. So I agree with you. I think that there are different type of investors that might have a different approach.
In that workshop that we did, we had from both sides, from the States and from Europe, not from us. Another aspect that was also commented there was neuroethics behind that, the neuro rights. Especially in the States, that is where it's flourishing much, much strongly.
Thank you.
Okay, well, we have gone on for quite some time, 1:10. We have a picoteo just across here. It's across the corridor, So if anyone would like to ask Jose some more questions, I invite you to go over, and let's just thank our speaker one more time for a brilliant talk.